Okay, welcome to lab 4 of 281. This is recorded and let's begin. So as far as announcements go, as always, auto graders are due soon. Make sure you do those. Make sure you do the quiz, the handwritten for lab 4. And the midterm is coming up October 21st, 7 p.m. It's never too early to start thinking about that. If you need accommodations, make sure you quest that. And as we get closer to the midterm, we're going to release practice material. So you should get plenty of resources to do as well as you want on this midterm. And please make sure that you have project due, the project 2 done, significantly before the midterm. If you use 2 late days on the project 2, you're going to be cutting into your midterm study time and everything's going to be stressful. So just try to get that done, give yourself a break, and then you can begin preparing for the midterm. Any questions on announcements? Okay, cool. So the agenda for today, first we're going to talk about the handwritten from last week. Then we're going to talk about priority queues, which are by far my favorite data structure. So I'm excited to talk about that. And then heaps and heap sort. And heap sort, kind of like priority queues, is probably my favorite sort because it kind of uses priority queues. And then we're going to go into set and union find and the handwritten problem. There's also a few slides about functors and tuples and pairs that we are not going into. If you want a reference for those, feel free to look at the lab slides. It's handy for the projects. Okay, so let's talk about the handwritten problem. To refresh your memory, it was anagrams. And the idea was to check if 2 strings are anagrams, which means that they contain the same frequency of characters. We gave you the constraint that these strings could only contain lowercase letters and spaces. This was a good constraint for you because that allowed you to use a vector of size 26 and index into that vector given the lowercase alphabetical character. But what if we didn't give you that constraint? What if your strings could consist of these angry emoji face people? Then how would you construct that vector? Well, I guess if you knew the constraints were ASCII values, you could make the vector size 126 or 256. But what if it could just be infinite? What if there could be endless characters involved? Then the solution doesn't really work as well. And we'll talk about how to handle this case when we talk about hash maps later on in the semester. So as for now, let's just talk about the case where it only contains lowercase letters and spaces. And let's go over a solution for that. Okay, so because we know that constraint, we can initialize a vector to be size 26. And then we can index into this vector and say that index 0 equals the character A, and index 25 equals the character Z. How do we get that? Well, we can use ASCII math and just take, the letter minus A. If the letter is A, then it will give us index 0. If the letter is Z, then that'll give us index 25. So we can use ASCII math there, which we can see here when we populate the vector. Then we go a second pass through the vector and we decrement for all the frequencies of the second string. And then at the end, we say, okay, we incremented for all the frequencies of the first string for all the characters. Then we decremented for all the characters of the second string. We can go through a third pass and say, now we're going to check to see if the entire vector should only contain 0, right? Because the first character frequencies should cancel out with the second character frequencies. If that's not the case, then we know that we don't have an antigram. So we can return false. If they all are 0, then we can return true. Any questions on this solution? It's worth noting that you can also do this in 2 passes. You don't have to do 3 passes. You could increment one string and decrement the other string in 1 pass. And then the second pass could just be checking to see if they're all 0. That might be a slightly more optimal solution. Okay, no questions. Let's continue. Okay, so to begin the content of this lab, we're going to talk about priority queues. And you can think of priority queues as this abstract container that supports 2 operations. First, we want to be able to insert items into this container. And then we also want to be able to remove an item where that item is the largest key or the highest priority item in the container. And that's really it. Today, we're going to talk about binary heap, really, and you're going to work with all these different types of heaps or priority queues in the project. So with the STL, what are the complexity of the priority queue operations? We list them here. Note that this is just a specific implementation of priority queue using a binary heap. If you implement a priority queue a different way, it might have different complexities. But push, pop are both log n, where n is the number of items in the container, and then top, empty, and size are all constant. Any questions on the STL's complexity for priority queue? Further on in the lab, we'll really dissect these operations, and hopefully you'll see why they are the way they are. Okay. So how do you actually declare a priority queue? We have the template class right here. Notice that it takes in 3 arguments. The second and third argument are both optional. If you don't declare them, then it will assign to a vector for the container and the less than operator or functor for the comparator. The default priority queue, if you did priority queue int, for example, will be a max heap. If you want a min heap, then you need to declare the comparator. So down here would be the declaration for a min heap. So max heap, would look something like this. Min heap would be below. The reason the reason that you don't have to declare those arguments for the max heap is because they are default. And then here we also say that the underlying container is used as a vector, as a second argument for the purposes of this class. And really, there's not a situation that you would ever have to change that underlying container to like a deck or a list. So you can just always keep that as a vector. Okay, so let's go into some practice problems. First, the question is, find the kth largest element in an unsorted vector. So if I give you this input of a vector that's not sorted right here, and then I give you k equals 2, you would return 6 because 6 is the second largest element in this vector. The first largest would be 7, 6 is the second. So let's talk about how we can do this. Whoops, let's get rid of that. Anyone propose a way that we could do this? Remember the operations for a priority queue. We want to be able to push to it, and we want to be able to pop. And when we pop, it's the top element or the highest priority element.
Could you just pop twice and then the second one that comes off is or like the kth one that comes off is the kth largest?
Yeah, exactly. So you can push all of these elements into the priority queue. And then, if the priority queue is a max heap, so the highest priority element is the largest element, then you can just pop k times, and the element on top is the one you want. Exactly. So that is approach one. You add them all to a max heap, then you pop k times. But what is the complexity of this?
I'm sorry, I have a question.
Sure.
You said you pop k times, so wouldn't how would it still be 6? Like I'm like trying to visualize that. And so if I pop first time, the 7 will come off, right? And I pop again, the 6 will come off. So how wouldn't the top be the 4th?
Yeah, that's a good point. So I guess for the implementation wise, it would be k minus 1, pop k minus 1 times, and then take top element.
Okay, gotcha.
Yeah, good catch. Anybody know the complexity for this? Well, it's kind of a tricky question. So what is the complexity to push an element?
Is it log n?
Yep, log n. So if we're pushing in all of the elements, it will be n log n, right? Because log n for each, and we're pushing in n elements. Everyone agree with that? Then what happens? What's the complexity if we pop, k minus 1 or k elements? What's the complexity of that? Well, the complexity for popping a single element is log n, and we would pop k minus 1 or k times, so it'd be k log n. So you could add those together, and you could get n log n plus k log n, and take the big O of that. And you could say that is the complexity of this implementation. But, right now, I am going to tell you something, and it's going to sound a little confusing, and we'll talk about it later on in lab. If you remember from lecture, you can actually add elements to a priority queue in O of n time. So rather than this n log n, we can do this in O of n right here. And the way we can do it in O of n is if we do initialization from a vector, and we have the beginning iterator for the vector and the end iterator for the vector, rather than an n log n operation, it becomes an O of n operation. So, just take that with a grain of salt. We'll talk about it in a little bit. If we can push all the elements and heapify them, turn them into a heap in O of n time, then this complexity with a better approach becomes O of n plus k log n and that would be our complexity. Any questions on that? Okay. So let's say that there's actually another way that we can do this too. Let's say that we're a little more constrained with memory. In this first situation, we throw in all n elements into our priority queue. So the memory of that is going to be O of n, right? N elements in the priority queue. What if I gave you an additional constraint that said, hey, what if we can only store k elements in our priority queue? Can anyone think of an implementation to solve this using only O of k memory? still using the priority queue, but now the max size of it is O of K. Or K elements. This is a bit trickier. So what if we threw in K elements? I guess the first question would be, okay, we have K elements in this priority queue. Is it going to be a max heap or is it going to be a min heap? We want to find the kth largest element. So what if we just had this invariant that the priority queue contains the K largest elements? Right? So let's say that our priority queue contains K elements, and those K elements are the K largest elements in our vector. Then could anyone solve that?
Oh, if you have only the K largest elements and it's a mid heap, then it's at the top, right?
Exactly. So if we constrain this to be a min heap, and we have the K largest elements in the priority queue, then our top element is going to be the Kth largest element, right? So then how do we get that invariant? How do we, promise that it's the K largest elements? Well, what if we just, iterate through this vector and we first store, if there's less than K elements in our priority queue, we add it to the priority queue, and the priority queue is a min heap. So we're here, and we add 6 and 4 because up until this point, there are, less than K elements in our PQ. So let's say our PQ is here, and it contains 6 and 4. How do I want to represent this? Let's just say that it contains 6 and 4, and 4 is on top, right? Something like this, 6 and 4, 4 is on top. Okay, then we go here. So what if we just let's just push every element and then pop the top one, right? Because if we push all the elements, the top one's going to be the smallest of all those elements, and we need to get back to our invariant of size K. If we push an element, it's going to be K plus 1. So then we can just pop it and get back to K. So if we just push the K first elements, and then for every additional element, we just pushed it and then popped the top one. Then at the very end, we would have K elements, and the top one would be our Kth largest element. You guys agree with that? So here, we push 2 in here, then 2's on top, and we pop the top element, and that gives us back to 4 on top. And then we go to here, we push 7, and now 4 is still on top, right? Because this is a min heap. 6, 7, and 4. 4 is going to be on top. So then we pop 4. So now it just contains 6 and 7 in our heap. Which one would it contain top? It would be 6 would be on the top. Then we get here. We have 1. We push 1. 1's going to be on top. Then we can just pop that because it contains K plus 1 elements. We want to maintain that invariant of just containing K elements. And then at the very end, after we pushed and popped every element after the Kth, the very end, we're going to contain 2 elements because K is 2, 6 and 7, and 6 will be on top. And that will give us our Kth largest element. Any questions on that? This representation is kind of confusing. I just wanted to say these are the elements in the container, and this is the element that's currently on top. Okay, so the second approach is to first add, the initial K elements into a min heap, And then after you add those first k elements, push and pop the remaining n minus k elements. This will maintain the invariant that the size of the PQ is always k. And at the very end, after you've done this, we're guaranteed to have the k largest elements in the PQ. Because if it was less than k, we would have popped it after we pushed it. And since it's a min heap, the top element is going to be the kth largest. So now the question is, what's the complexity of this solution? And I will tell you now, actually, no. Yeah, what's the complexity of approach 2? We can break it down into steps. So the size of the PQ is going to be k. So if we push and pop elements, it might be 2 log n or 2 log k or log k, but every push or pop is going to be log k. And how many times are we going to push or pop? It might be 2n, n, but it'll be on the order of n. So for this solution, since the priority queue only contains k elements, the operation will be log k. And then how many elements are we pushing and popping? N log k. So going back to that initial approach, oops. Weird. Going back to the initial approach was O of n log n. Or actually, sorry, O of k log n. And second approach is O of n log k. Which one's faster? Well, k is always going to be less than n. So the second approach will be faster. But the first approach will be better on memory, right? Because the first approach is going to be, the first approach will always be faster, but it's going to be worse on memory. It's going to be O of n memory. Where the second, which will be slightly slower, is O of k memory. Kind of a confusing example. I recommend that after lab, you go back and try to prove this to yourself. Any questions on that? Okay, cool. So now let's talk about heaps and heap sort. And when we talk about priority queue, at least up to this point, we've been talking about binary priority queue, which are implemented using heaps. So let's talk about the implementation of this actual priority queue. First, a max binary heap is a binary tree with these two properties. First, each node has an equal or greater priority than its children. Another way of putting that is no node has a lower priority than its children. So it's either equal to or greater than. So that's the first property. The second property is that the tree is complete. And what does that mean? It means all levels of the heap are full, except the last, potentially. And the last level must be filled left to right. So for example, let's say that this tree has 3 levels, something like this. They're all full, except the last one isn't, there's only 2 nodes, but it's filled left to right. So this is a valid complete tree. But if it looks something like this, this would not be a complete tree because the last row is filled right to left. Any questions on these two properties? So this is valid, this is not. If we got rid of those, this would also be a valid complete tree.
Wait, sorry, can you explain the left and right thing one more time?
Yeah, sure. Okay, so it says all levels of the tree are full, except potentially the last. But for that last level, if it's not full, then it must be filled left to right. So let's say that our last level is 3. There's going to be 3 levels in this tree. This one, let's say that's not full. It would be full if it looks something like this. That's complete. But if it's not full, if we don't have 4 nodes in this last level, then those nodes have to be filled in left to right. So this would be invalid because there's a gap. But if we put that back, this would be valid because there's no gap. It's filled left to right. Make sense? This would also be valid, still filled left to right. This would not be valid because there's a gap on the left. Cool. All right. And I think in the next slide, you'll see why we care that it's a complete tree. Okay, so oftentimes trees are implemented using arrays. So if you look at this tree right here, you can represent that tree using this array, where the first element is the root, second element is the left child of that root, 19, and the next child, and then it kind of goes, pretty much just goes like left to right. So now you can kind of see, if we want that ability to represent trees using arrays, we need those trees to be complete. For example, let's say that on this last row, it looks something like the 2 was here and the 7 was here. Just looking at that tree, we would have no idea, or sorry, just looking at the vector, we would have no idea how to represent that tree. Because these last 2 elements, where are they in the last level? By requiring that they are filled in the tree left to right, then we can look at this vector and say, yes, it must look like this tree, where that last level is filled from the leftmost to the right. Make sense? So, some questions on this. If we're looking at this array, if we're looking at the position I in the array, how can we conclude I's parent? What math can we do? So let's say that we're looking at the third element, or I guess this would be the second index, zero-based indexing, and we want to find its parent. Well, 36's parent is 100. So can you guys think of the math that you would do for the ith element to find its parent? I divided by 2, exactly. Oh, shoot, wrong one. What? I minus 1 divided by 2. I think this is assuming 1-based indexing. But yeah. So I guess if I is 2. Oh, actually, you know what? No, for 0-based indexing, it would be I minus 1 divided by 2. For example, if our index is 2 and we want to get its parent, which is 0, if it was just 2 divided by 2, that would give us 1. So we have to subtract 1, I minus 1 divided by 2. So it'd be 2 minus 1, which could be 1 divided by 2. Integer division would give us 0. So if we're doing 0-based indexing, it's I minus 1 divided by 2. And then what are the indices for the children? So if we're looking at the ith node, how do we find its left and right child? In this case, I guess 25 and 1. Neil says I times 2 and I times 2 plus 1. Well, okay, so if we look at 36, this gives us an index of 2, right? And its left child would be index of 5, and its right child would be index of 6. So what you do, it would be I times 2 plus 1 and I times 2 plus 2. Plus 1 for the left, plus 2 for the right. I believe that you're doing 1-based indexing. Okay. Now here's a good practice question. So on the exam, this might be like a practice question you would see on the multiple choice for heaps. So given these 3 representations of heaps, which ones are min heaps and which ones are max heaps? I'll give you a second to think about this one. One way that I typically do this is I look at this element that I say, okay, what is this element's children? Well, 1's children are going to be 8 and 4. Is it greater or equal to priority of its children? Then I'll look at 8 and I'll say, what are 8's children? Well, they're 9 and 12. And I'll continue down and see if it's a min heap or a max heap based on the priority, or none. And remember, with priority queues, the invariant is each node is no smaller in priority than its children, or another way of saying that is each node is greater or equal priority to its children. What is priority in the max heap? Priority is the largest element. In the min heap, priority is the smallest element. Okay, anybody have any answers for this? I guess first, which one's the min heap? A, I agree with that. So A is the min heap. So when we think about min heap, priority is smaller. So we have to see if any of these has a situation where the current element is smaller or equal to its children for all of the cases. So if we look at A, when the current element's 1, is 1 smaller or equal to its children? Is 1 smaller than 8 and 4? Yes. Then we go to 8 and we say, okay, is 8 smaller than its children? Its children are 9 and 12. It is. Then we go to 4 and we say, is 4 smaller than its children? 11 and 7. Yes. So this is min. Okay. What about max heap? Which one or ones are max heap? C and D. I agree with that. And similar for min, max, we would just go to every node and say, okay, is this node at least as large as both of its children? Is it no smaller than its children? If that's the case, then we go on to the next one. And we continue to do that until we checked every node. And if the constraint holds, then it's a max heap. Any questions on this? Or do you guys want us to go through C or D? Why isn't B a min heap is the question. Okay, let's go through it. So if it's a min heap, then every node is no greater than its children, right? In other words, every node is less than or equal to the size of its children. So let's look at 3. 3 is the first element, and its children are 4 and 5. So we're good so far. Its children are greater. Now let's go to 4. Its children are 7 and 12. So far, so good. Let's go to 5. Its children are 11 and 8. We're good here. Let's go to 7. Its children are 6 and 13. So 6 is less than 7. So therefore, it's not a min heap. Cool. All right. And that's what you guys said. Good job. Okay, so that's heaps. Min heaps, max heaps. Now let's talk about how we can actually maintain this heap property. So let's just talk about single elements right now. So let's say that we have a heap, and then we suddenly increase the priority of a node in the heap. So if it's a max heap, let's say that we have a given node and we say, okay, if it's a max heap, we increase its value. It goes from 5 to 10. How do we maintain the heap? How do we adjust the tree so it stays a heap? And when we increase the priority, we call fix up on that node. And what does fix up do? Well, it continues to swap the node with its parent until we're either at the root, therefore it can't swap anymore, or the parent has a larger or equal key to it. So pretty much another way of saying this is while the node's parent is smaller or lower priority than it, swap it with its parent. And then the base case is if you're the root, you can no longer swap with your parent. So what's the complexity of this? And I guess I should say, what is the worst case complexity? Anyone? Log n, exactly. The worst case complexity is log n because these trees are balanced trees. And how many levels are there in a balanced tree? Log n levels. So at most, when you increase the priority of a node, it's going to move up log n positions. And a quick example of that is, let's say that this node right here, let's say that we have a max heap. And we increase the value of this node from 7 to 16. So its priority is increased because this is a max heap and we increase the value. So now what do? We continue to swap it with its parent until its parent is no longer higher priority. Or sorry, until it is no longer higher priority than its parent. So we look at it, 16, its parent is 10, 16 is higher priority than its parent, so we swap it with its parent. Okay, then we look up at its parent, 15, 16 is higher priority than its parent, so we swap them. And now we hit that base case where 16 is now the root, so we don't have a parent, and we call it there. So after increasing the value of the node, we call fix up, and this maintains the heap. Question?
Yeah. Why
Yeah.
is the number of levels in the heap log n by any chance? Maybe it's something that I missed.
No, that's a good question. So why is the number of levels in a heap log n? Because a heap is a balanced tree. Remember when we talked about a heap has to maintain that property that's a complete tree?
Yeah.
What that means is the tree is balanced. And I think we'll talk about what balance means maybe later on. But essentially, with binary trees, they're always filled in like this with heaps, right? Like every time I add a node, it would look kind of like being filled in like that. Agreed? Because it has to be complete, every row is full. The one that's not is going to be filled in left to right. And because it's a binary tree, every node can only have 2 children, its left child and its right child. And you'll see that when you look at these complete trees, when it's complete, the way that each level increases is exponential. So we have 1 node on the first level, we have 2 on the second, we have 4 on the third, we have 8 on the fourth. And then if this was full, we would have 16, right? So let's say that this node, we increase its priority, it could potentially move all the way to the top of the tree, right? So then how many levels are there in a balanced tree is the question. And the number of levels in a balanced tree is log of the number of nodes in the tree. Or log n. And that just comes down to a tree at every level gets exponentially larger. Right, because, if we have, 2x and we take log of 2x, that gives us x, where x represents how many levels are in the tree. Does that make sense at all? I don't think I explained that too clearly.
It made some sense. Yeah.
Long story short, a tree gets exponentially larger at each level. So if you're trying to figure out how many levels there are in a balanced tree that's getting exponentially larger, you can solve for that exponent. And the way to solve for that, where x is the level in the tree, you would take the log of that. So
Gotcha.
When you have a balanced tree, if you take the log of the number of nodes in the tree, you get how many levels there are in the tree. Okay. Okay, so now let's talk about decreasing priority. So let's say that we have a node and we decrease its priority. How do we maintain the heap invariant? Well, what we do is we just swap it with its largest children until its children are no longer higher priority than it. So similar to fix up, what's the complexity of this one? We have a balanced tree. And I guess, if we're swapping with its children, at most, we're swapping with all of the levels in the tree, right?
Would it still be the same?
Yep, it would still be log n, where n is the number of nodes in the tree. And to go through a quick example of this, let's say that we're looking at a root and we decrease its priority. So this is a max heap. And let's say that we decrease it to 7. Now its priority is lower. I'm just going to erase that. So we swap it with a child. Well, I guess first off, we look at its children and we say, is our current node lower priority than either of its children? And we look and we say, well, it's lower priority than 10, but it's not lower priority than 6. So it's lower priority than one of them. So we swap it with one of them. And then we look at its child again. Is it lower priority than its child? No. So we stop there. But what if it was lower priority than both of its children? Like, let's say that it's 7, we switched it from 15 to 7, and now it's lower priority than 10 and 8. What we would do is you make sure that you swap it with that largest value child. So if both of them are higher priority, you swap it with the highest priority. And the reason you swap it with the highest priority is because you're liable to lose your heap invariant if you don't. If you swap it with the lower priority child. Trying to think of a way to show that in an example. But yeah, just take my word for it. If both children have greater priority, swap it with a higher priority child. Okay, so any questions on that between fix up and fix down? Do both of them make sense? Okay, I see why. So the reason why you have to swap it with the highest priority child is because, let's say in this case, we swap it with 8 rather than 10. When we swap it with 8, it looks something like this. This is no longer a valid heap, right? Because 8 is not higher priority than 10 in a max heap. So if both of the children are greater priority, swap it with the higher priority child. Okay, any questions on that so far between fix up and fix down? Now we're going to talk about how those apply to a heap. So how do you insert an element into a heap? Well, we can just insert it at the bottom of the heap. And now that we inserted an element that didn't exist before, of course, it's going to be like increasing its priority. So we could just throw it in at the bottom and then call fix up, because it has a higher priority than it did when it didn't exist, now that we created it. So that would be one way of inserting into a heap. And that's going to move it into its correct position in the heap. Any questions on heap insertion? You know, like when our heap was this, if we wanted to insert a new element, say 30, just throw it in at the bottom. It would actually be thrown in over here because we have to have that complete tree. And then now that we threw in this new element, we just continue to call fix up until it reaches its correct position. And that in this case, it would have done something like this. And that would be like inserting into a binary heap. Then similarly, if we're removing from a binary heap, we would just, it's a little more confusing. So when we remove from a binary heap, remember, we only have access to the top element. So we only have access to the root. So when we want to remove an element, really what we're saying is we're removing the root. And one way to remove the root is to swap it with the last element in the heap and then delete it. So switch the root with the last element, delete the root, and then now your last element has a lower priority than it did before, right? So you can call fix down because its priority is now lower, and that will adjust its place in the heap. Is there a place for an example for that? So to give you an example of that, you know, if we have, let's say we have a max heap right here. Let's say we have 5, 4, 3, 2. And we want to remove the root. So what we can do is, I guess, okay, first question is, how is this represented in a vector? This tree that we have here, this heap. Because I think it'll make it more clear why we swap it with the last element. Anyone? What is the representation of that tree in a vector?
Five, 4, 3, 2.
Yep. So 5, 4, 3, 2. And now we want to remove 5. 5 is at the front of the vector. You know, we can only pop from the back of the vector, right? So we're saying we want to move 5 with the last element. Then what that would do is the vector representation, can't move it. The vector representation would look something like this. Then we can pop back the last element. So that makes it easy to remove it. So that's why we swap it. Swapping it lets us pop back from the vector. And now that we swapped the top element with the back element, you know, we clearly decrease the priority. This element that's now at the root has a significantly lower priority than it did before, because before it was the root and now it's the last element. So after we decrease the priority, like we said before, we call fix down. So fix down on this, you know, 2 would have a lower priority than both its children. So you'd swap it with the highest priority child, and that would fix your heap. And that's how you remove an element from the heap. Any questions on that? And that would look something like this. So when you add, you add the element to the end, you call fix up on that element. When you remove, you take that top element, you swap it with the last one, then you delete the last one. And now you call fix down on that new root. Cool. Okay, a question for you guys. So we're going to start with an empty max PQ, and then you're going to insert all these elements into it. And then you're going to delete the most extreme element twice and give what the array looks like. So when I approach these types of questions, I would just do it step by step. I would write it all out. So I'd start with an empty heap and then write out what the tree looks like every time I insert an element. And then I would delete one element, see what the tree looks like, delete another element, see what the tree looks like, and then take that tree and translate that into an array. And that should be your answer. So I'll give you guys a few minutes to do this. It'll take a bit of time, and then we can reconvene. Also, feel free to ask any questions that you have for solving this problem. When you get an answer, feel free just to post it in chat. And there is only one answer. Anyone have anything? Any ideas? We have a D. Any other ones? Two for D, and I agree with that. Nice. Do you guys want to walk through this too? Okay, yeah, let's walk through this one. So we have this max PQ and we insert these elements. So first, let's just insert 14. And then let's insert 4. So far, so good. We don't have to call fix up. Then insert 5. Still maintained in a heap. Insert 26. Now, or 23 rather. Now that we inserted 23, our heap is no longer maintained. So we have to call fix up on this. When we call fix up, we move it with its parent. because its parent's a lower priority than it. Then we move this one with its parent because the parent's lower priority. Okay. And now we insert 9, the next place we would insert, because we have to maintain that complete tree, is under the 14. Okay, we looked, we call fix up, we're good. Nothing has to happen because its parent is higher priority than it. Okay, then we throw in an 11, we call fix up. 11's greater priority than its parent, so they switch. And it's no longer a greater priority than its parent, so we're good there. And then we throw in 2. 2 would be right here, and that's good there. Okay, so that would be inserting the elements into the tree. And now we have to remove the most extreme element twice. So just like we said earlier, we swap the root with the last child. Then we delete the old root and we call fix down on the child. This is lower priority than both of its children. So we swap it with its higher priority child. And then we do that again. So after the first remove, the tree looks like this. And now we remove one more time. So just like we did before, we swap 14 with 5, remove 14, call fix down. This swaps with 11. And then we're good. And that's the answer. So now we can just go through this and get the array representation. To do that, we could just go left to right and get 11, 9, 5, 4, 2, D. Make sense? Okay. So that's that. Now let's talk about heapify or make heap. So given, an array, how do we turn that array into a heap? Well, the first way we could turn this array into a heap is we could just start with an empty heap, like we did in that previous example, and insert the items one element at a time. Every time we insert an element, call fix up, and then it will maintain the heap and do that for all the elements. With this approach, what would the complexity be?
Log in or n log n.
Sure. Why do you think it'll be n log n? That is correct, but why?
Because every time we call fix up, it's log n complexity, and we're doing it n times for each element that we're pushing.
Yeah, exactly. We have to push n elements. Each time you push an element, it's log n, because worst case, it has to go up the entire tree. It gives us a complexity of n log n. Perfect. And this kind of brings us back to that problem we did in the very beginning, where I said, this was the first approach, the way to do it, but there's a more optimal way to do this, where we can actually heapify a vector in n time rather than n log n time. So let's talk about that approach, that second approach. So what if you just started with an you started with a unsorted vector, and you have two ways. So let's say that you have an unsorted vector. You could either iterate left to right in the vector, calling fix up, or you could iterate right to left, calling fix down. And that's essentially the same thing as, let's say that you have a tree that's unsorted. I think we have it here. Yeah, so here's our tree, it's unsorted. We could go from top to bottom calling fix up. So we could call fix up on this element, then this element, then this element, then this one, then that one. And every time you call fix up, it might move up the tree. That's one approach. And that's like if you had the vector going left to right calling fix up. Another way that you could do it is if you have the tree and you start at the bottom and you call fix down. So you go essentially in the vector right to left calling fix down. Those are the two valid ways that you could use fix up or fix down to heapify a tree. the other two possibilities wouldn't work. You couldn't go top to bottom calling fix down, or you couldn't go bottom to top calling fix up. So given these two methods, right, repeatedly calling fix up starting at the top or calling fix down starting at the bottom, which is better?
I'm assuming fix down because we just spoke about fix up and you said we're going to learn a better way to do it. So
yeah, so fix down is better. And I know in lecture, you guys kind of go through like a little proof on it. I'm not gonna go through a proof, but I'm gonna try to like show you why it's better, just conceptually. So, and actually, yeah, so it is better. Method 2 is O of n, and this method is n log n. So it's significantly better. So let's see why. Here's our tree, right? And it should be a max heap, but it's not yet. So we have to heapify this tree. And I told you that there's two ways that we can do this. We can start at the top element and then go down like this, calling fix up. Or we can start at the bottom element, going to the top, calling fix down. And let's talk about each of those. Also, this is a good tie back to when we have these trees. Actually, okay, so when we have these trees, we talked about the worst case being log n for fix up or fix down, right? And the reason the worst case is log n is because log n, where n is the number of elements in the tree, log n is the number of levels. And fix up or fix down, the node could potentially travel the number of levels, right? So that's the worst case complexity for fix up or fix down, log n. So given this tree, if fix up and fix down are both log n operations, worst case. Well, actually, let me back up a little bit. Fix up and fix down are both log n operations, worst case. But let's say that we're at the bottom of the tree, this node right here, and we call fix down on it. It's not going to be log n, it's going to be O of 1, right? Because there's no elements below it. Even kind of with these nodes, like if we call fix down on this, there's no way it's going to travel more than one position. So it's not really log n. It's really only gets to log n, when you get closer to the root, right? Like if we call fix down on the root, that's going to be log n because you're going to have to go all the levels potentially. But at the bottom of the tree, fix down is not really log n. Everyone agree with that?
yes.
You can make the same observation, fix up. For the first node, fix up's not really log n. It's kind of just O of 1. With the second row, fix up's really not log n. It's just kind of potentially 2 steps. It's only really log n when you're at the bottom. So that's the first conceptual hurdle, is saying that like fix up or fix down is different depending on where you're at in the tree. And if you're at the bottom and you're calling fix down, it's pretty much constant. So now let's talk about the property of trees. Because trees are exponential, whereas each level is double the size of the previous level, half of the nodes, if n is the number of nodes in the tree, essentially half of the nodes are in the last level of the tree. So trees are very bottom heavy. Most of the nodes are in the very last level or the second to last level. So going back to this fixed down idea, if we have the option of doing no work on half of the nodes in the tree, that's pretty ideal. If half of the nodes in the tree fixed down is O of 1, that sounds nice. I mean, so let's talk about the first approach. Let's say fix up is O of 1 for one node in the tree, or fix down is O of 1 for half of the nodes in the tree. That sounds like conceptually far different as far as work done, right? So because trees are bottom heavy, you want to do it right to left calling fixed down. Because then you're barely doing any work for half of the nodes in the tree. And you could even say like the nodes above that, you're doing a lot less work for those nodes. Does that make sense conceptually for you guys? Do you guys understand where I'm getting at here? To minimize work, we'd rather call fixed down right to left than call fixed up left to right.
Makes a lot of sense.
Awesome. And that's the reason that it's O of N when you go right to left, calling fixed down. So if you're on the exam, you're trying to think like which one's better, just think like you want to minimize work. And if you start at the bottom calling fixed down, that's going to minimize work because it's a constant operation for the last row. Cool. You guys don't worry about like memorizing the formal proof for it. We don't test that in this course. Great. So just as a summary of making heaps, calling fixed down, starting from the bottom, has a complexity of O of N. Calling fixed up, starting from the top, has a complexity of N log N. And that's heaps. So let's talk about heap sort and then take a quick break and then talk about unified. So now that we have this idea of heaps where, the highest priority item is on top, and you can insert items into the heap, let's think of a way to do a sort given those properties. So we're going to use heaps to sort. And how are we going to do that? Well, if we know that the highest priority element's on top, let's just take that element out. That's sorted. And then fix the heap. And now the second highest priority element's on top. Let's take that one out, fix the heap. Now the third highest priority element's on top, take that out, fix the heap. So keep on extracting the highest priority element until there's no more heap. And as you extract those, you're essentially sorting the elements. So let's go through an example of that, and then we'll go back to the complexity. I think that an example will make this a lot more straightforward. So here's our tree, and it's currently not a heap. What's the array representation of this tree? Well, we go left to right. So 5, 1, 8, 4, 3. We know this isn't a heap. So if we're going to do heap sort, the first step is making it a heap. Build a heap, remove items. So let's make this a heap. How are we going to make this a heap? Well, we just learned that we could go from the back calling fixed down. So let's do that. So start at 3, call fixed down. That doesn't move. Go to 4, call fixed down. That doesn't move. Go to 8, call fixed down. That doesn't move. Go to 1, call fixed down. It does move. It switches with 4 because 4 is the highest priority of its children. Now we go to 5, call fixed down. Higher priority than 4, lower priority than 8. So now we have a valid heap. Everybody agree? And we just made this heap in O of N time using the method that we just learned. Cool. So we want to sort this array. Here's our array representation of our heap right now, right? That's not sorted. We want to make this sorted. And we said, the first observation is we know the top element, because it's a heap, is the greatest element. So an observation that we can make is if we throw this element to the back, if we pop this element from the heap, what's going to happen? Well, this 8 will go here, right, to the last element, and the 3 will go to the root. And what will that look like in the array representation? The 8 will go to the last element, and the 3 will go to the root. look at that. A is now in its correct position. That makes sense because we're throwing it to the back of the vector, which is essentially the last element in the vector. And now 3 is the root. So because A is in its correct final position in the array, let's just pretend like it no longer exists, that it's disconnected from the tree, that we popped it, but not really. And in the array, it would look something like this. So now that we swapped 8 with 3, obviously this is no longer a heap, so we have to reheap it. We have to heapify it. So 3 is going to switch with 5 because we're calling fixed down. And it would look something like this. Right? Everybody with me so far? Essentially, all we did was we popped the top element, but we didn't actually pop it. We're just like pretending to pop it. Any questions so far? Okay, so now we're going to continue this. Notice now, we removed 8, and now the second largest element from the original tree is on top. So, we want to put that in its final place. How do we put that in its final place? We did what we did before, and we pop it from the tree. So we're going to do is we're going to switch it with the last element in the tree. Remember, we're pretending like 8 is no longer the tree because in the array, it's in its final position. So we're going to switch it with 1 rather than 8. And what's that going to look like here? It's going to look like this. And now, like we did with 8, let's pretend that it's no longer there. Disconnect it from the tree, from the heap. Of course, now that we put 1 into the root, we're going to have to call fixed down to maintain that heap invariant. So we're going to look at both its children. They're both greater priority. So we're going to switch it with the highest priority child. And now, do we keep on going? No, we don't, because 1 no longer has any children, and I say that with like air quotes because of course 5 and 8 are still there, but we're going to pretend that they're not there because in the array, they're in their correct final position. Okay. So now, we have 3 more elements in our tree, or 3 remaining elements in our tree, and it's a heap. And we just repeat the process. Of the last 3 elements, the greatest element's on top. So we pop that element, and by popping it, we move it to the back of the tree and then erase it. What does that look like? Oh, shoot, I didn't update the heap. Here, when we updated the heap, this would be, the array would look like this. The array representation, 4, 1, 3. So now when we pop it, switch it with 3, disconnect it, and in the array, it looks like this. Okay, we switched it with 3, now we call fixed down. 3 only has 1 child now, which is 1, and it's greater priority than 1, so it stays in its location. And now we pop 3. The way we pop 3 is we move it to the back. The back is now 1. And then we disconnect it. What does that look like here? I'm sorry. Switched it with 4. 4 is disconnected. So 3 switches with 1. And then we disconnect it. And now, since there's only 1 element remaining, we're done. And you can see we have a sorted array. Any questions on that? So in summary, we're using the property of heaps because we know the greatest priority elements on top. We use that property to constantly pop the top element, disconnect it from the tree, and keep on rebuilding the heap, popping the top element, rebuilding the heap, popping the top element, until the vector representation is a sorted array.
So when you're popping, because you were saying like we're pretending that we're popping. So when you're popping, is not really going away, or like when you pop or before you pop, you're like putting it in an array. Is that like?
So the way that I would think about this is, we imagine these heaps as trees, but really in the underlying code, we typically represent binary heaps as vectors. So when we represent binary heaps as vectors, typically when we pop an element from the heap, after we swap that top element with the last one, we would call pop back on the vector, the underlying vector, right? To remove the old one.
Yeah.
But I'm saying here, we're not actually calling pop back on that underlying vector. And the reason we're not calling pop back on the underlying vector is because we want to store that underlying vector as a sorted vector. That's the whole purpose of this, is we want to take an unsorted vector, heapify it, then sort it. So because we're not actually popping from the vector, because we want to store that information, we're just like I said, we're like pretending to pop. We're just moving the indices, like the ending of the vector, to be smaller and smaller so that our heap is shrinking, but we're not actually calling pop back on the underlying vector. Does that make sense? So, like you could store like an additional element called like end of vector. And end would constantly be incrementing, but we would never actually be calling pop back on our vector.
Gotcha.
Interesting. It's an interesting concept to try to like wrap your head around. It's like, okay, I got these heaps. I'm understanding how priority queues work. Now, after that, you take the branch and saying like, okay, priority queues are represented as arrays. And then from there, it's like, okay, now that I know that they're represented as arrays, how can I manipulate and play around with like how this representation is to take an array and turn it from an unsorted array to a sorted array using heaps. And that's like the final step. So now that we have this, let's talk about the complexity of this. So heap sort. What's the first step, guys?
Heapify.
Yeah, heapify. What's the complexity of heapify?
I believe because we start from the bottom, it's O of n, right?
Perfect. Yes, O of n. Then step two. What's step two?
Up the top.
Yeah, let's say for n elements, we do what?
Pop the top.
Pretty much, yeah, pop top. And then what? Yeah, pretty much pop top. Pop top under the hood, swapping and then calling fixed down, right? So what is step two? Complexity.
N log n.
So n for n elements, and then it's a log n because each fixed down log n, right?
Yeah.
Nice. So together, the complexity is O of n plus log n. And that's heapify. That's a heap sort. So you can sort any unsorted vector using heaps, and get a complexity of O. Sorry, there should be another n in there. You can get a complexity of n log n. And that is a very good sort, n log n, the fastest you can get it on sorts, given no additional information. Cool. Let's take like a 2 or 3 minute break real quick. This is a long lab, so let's just take a little breather and then reconvene. Get some water, stand up, walk around a little bit, and then we'll get back to it. Also, feel free to stay around and ask me any questions if you have any. All right. Everyone ready to get started? Talk about sets and union find. Everyone's favorite topic. I think traditionally sets and union find come across as pretty intimidating because it's a difficult concept to understand, but I think that like, don't be intimidated. The implementation itself, the code itself is very, very straightforward. Once you understand the conceptual hurdle, it becomes far less intimidating. Cool. So let's get started. So quickly on sets. A set is just a collection of objects. And you only check one thing. Is the object in the set? So because of that, all of these sets right here are the same set. They all contain 1, 2, and 3. We don't care about duplicates. And yeah, the empty set, blah, blah, don't care about that. 203. So with sets, you have set operations, right? You remember this, you got the union, you have set intersection, set difference, whereas set union is just all the objects that are members of one or the other. Intersection, all the objects that are members of both set 1 and set 2, and set difference, all the objects that are members of one but not the other. So let's just go through a quick rundown of what that would be for these two sets, set A and B. I guess first, feel free to answer, what is the set union of A and B?
One, two, three, 5.
Exactly. You know, one or the other. So just the collection of all of them. What about the intersection?
1, 3.
1 and 3. Yep. Whatever elements are in both of them. And then what about the set difference?
Just 2.
Just 2, right? Whereas, you know, what elements are in A but not B is what that means. And only 2 is in A but not B. Okay, so that's just a little review on set operations. Good practice for you guys is how would you actually implement these operations if you had 2 sorted vectors and 1 output vector? So let's say you have a sorted vector A, sorted vector B, and you have an output vector and you have to find the union and throw that union into the output vector. These are common exam questions. You'll see it once you get to the practice problems. We like to ask you questions like this, like how do you find the set union of these 2 vectors or the intersection or the set difference? So that's something that you could implement on your own time and think about. Here are the explanations for those 3. I'll let you guys go over that on your own. But definitely think about that for the exam. So now let's talk about set operations. How do we know, if 2 elements are part of the same set? So here we have A and B. They're not part of the same set, but how can we figure out whether or not they are? And that's really where union find comes into play. When you have 2 disjoint sets and you want to figure out if items are in the same group, or not even just 2, if you have disjoint sets and you want to figure out if items like A and B are in the same set, that's where you want to use union find. And essentially union find is just 2 functions. You have union and you have find. And then you also just need to represent, your items in your set using a vector or something, and that's it. Each item has a representative to say which group that item is a part of. So here, imagine all the people are items in the set. And we have 2 sets, right? We have the US citizen set and we have the Canadian citizen set. And how do we figure out if, two people are in the same country or the same set, well, we just look for the representative. This dude's representative, his leader might be this dude, but this dude's leader is, I guess, the king of the US or queen of the US. So just following up their representatives, we know that this person is in the US. Similarly, we can look at this person, figure out their leader, what their representative is, turns to this guy, figure out what his representative is, or her. And it goes to the Canadian king queen. So from here, we can say, okay, this person is a citizen of Canada. And like I said earlier, each item or citizen in this case has a representative to identify the group that they're in. Does that silly example make sense? Figuring out the group you're in from your representative, which ultimately leads to the crown person. So now that's essentially find. You're finding the representative of a citizen. How do you know if two groups, how do you combine two groups? That's for union. So how would we combine these two groups? Well, we could union together these two people and say, hey, how about this person just points at that one? And if that's the case, what we did was now all of these people also point at that one indirectly, but still do. So that's how we union these two sets. So right now, we have these two disjoint sets. If we want to union them, you just take the leader of one set and point it to the other one. Originally, maybe it's pointing to itself, but we just point it to the other set. So that's union. But this isn't that optimal, right? If we want to find what set this person's in, what are we doing? Well, we go here, and then here. That's pretty slow. Then I'll say we want to find which group that person's in again. We'd still go here, then here. So we want to use this idea called path compression when we're doing this union find operations. And the idea is, if we call find on this person, for example, this guy, it gave us the ultimate representative here. In the future, rather than having to go up that tree again to find its ultimate representative, we could do this thing called path compression to just save some work and point it directly at that guy. Then when you call find on this person again, they'll point to the leader initially, rather than having to work your way up the tree. And that's the idea with path compression. Every time we call find on an element, we move the element closer to its ultimate representative to reduce work. And that's all path compression is. So now we have three concepts, right? Ultimately, we're using union find to try to figure out if elements in disjoint sets are in the same set or in a different set. And then we do that by calling find on the element to figure out its ultimate representative. And in that find operation, we can use path compression so that we only have to do the work once. And then union is another operation if we just want to combine two elements into the same set. Everybody following along so far? It's really just those three concepts. So how do you represent path compression? So here would be the code. It's recursive. It's kind of confusing. I'd recommend that you guys go over this on your own time, looking at the code, convincing yourself that you understand it. But this essentially is your find operation that also implements path compression using recursive stacks. And what does that look like? When we call find, if we use path compression. Once again, let's say we call find on this guy. Then, we look at its representative. We look at its representative, and we get here, finally. And we say, okay, this person's ultimate representative is up here. But if we use path compression, after we figure that out, instead of pointing it at its old parent, we point it at the group leader. And for all those parents along the way, we also point them at the group leader. And this person also points at the leader. So now, if we call find on this person again, it just goes directly to the group leader. So it's a much faster operation than it was before. Similarly, this would also be a faster operation if we call find on this leader or this person, because rather than pointing to the next person, then the leader, it just points directly to the leader. So we updated essentially all the people in the path to point directly at the leader rather than their parent using path compression. Cool. So let's transition that to now looking at like a solid implementation of this. So here we have a vector where the index represents the node. So index 0 represents 0. Index 1 represents 1. Index 2 represents 2. Index 3 represents 3. And index 4 represents 4. And then the value at that index represents what its representative is, what it's pointing at. So for example, index 4, its value is 3. So it's saying node 4 points at node 3. Here it says index 3 points at node 2. Node 2 points at node 2. So this would be like this. Okay. So here's like another way to represent, the tree that we were looking at before in a concrete example. I guess I want to stop here. Everyone understand how we can use really just one vector to represent this structure, where like the index represents the node and the value at that index represents the node that it's pointing to. Any questions here? Cool. Okay. And now if we call find of 4, so we're saying we want to find the ultimate representative of 4. What would we do? Well, we'd look at 4, either in the vector, or I guess we could look at the diagram, but we look at 4 in the vector and we say, okay, what's its representative? 3. So now we look at 3 in the vector. What's its representative? 2. Now we look at 2 in the vector. What's its representative? 2. So now we know that 4's ultimate representative is 2, right? Because 2 points to itself. And you can see that with the visual below. So if we call find of 4, we would return 2 because 2 is 4's ultimate representative. And without path compression, we wouldn't modify the vector. If we use path compression, what would this vector look like after calling find of 4? What would this look like after calling find of 4?
Would it go directly to the 2?
Yeah, but how do we actually show that in code? Like, how would we implement that? I guess visually, you were saying it would go directly to 2. Yep, and 3 would too. But in code, what would that be? Well, 4 would be 2, right? And 3 would stay 2. So that's what it would look like with path compression. But in this example, we're not doing path compression, so it looks like this. Okay. And then here is some code for how you do the find operation without path compression. Not that you need to really reference that. So a question for you guys, what is the complexity of find without path compression? What's the worst case?
Oh,
Yeah, why is that?
Because worst case, we have to like search. Is it considered searching through like in different? Um,
Yeah, exactly. So let's say that, we want to find this person's ultimate representative. And what if it's just like this long list of n elements where we have to iterate through the entire list until we get to its ultimate representative? How long can that list be? N elements. So we get O of n. And that's the worst case. However, what if we use path compression? Well, then you're still going to have this worst case potentially, right? You might get it one time. But then after you have this worst case, if we call find with path compression, this list would then look like this, right? Using path compression. So now the worst case would no longer be O of n. Now it would be O of 1. So that's why path compression is so powerful. You're doing a bunch of work one time maybe, but then after that, it becomes very, very quickly. Very, very quick. So you can see this here with the code. The worst case of find x. Here we have that example where, say we want to find 4. 4 points to 3, 3 points to 2, 2 points to 1, 1 points to 0, and finally 0 points to itself. So we had to iterate through all of the elements to figure out that 4 ultimately points to 0. But using path compression, after we did that find once, then you can see that we update everything on the path now points to 0. So calling find now would be O of 1. Any questions?
Wait, sorry, can you explain one more time why you update everything to 0 instead of just the one that 4 points to?
Sure. To make this clear real quick, let's go to this example where we're calling find on this person, right? When we call find on this person, we figure out that their ultimate representative is this person. So we update its ultimate representative to that. But we could just stop there, but we have additional information. We also know that every person on this path also points to that same ultimate representative.
Oh, okay. Thank you.
So you could do additional work and say, hey, how about we set all of those people to 0? Because we can, and it's going to be really efficient. All those people to the leader. And that's the same thing here. If they're all pointing on the path, you can set them all to the last element in the path. Cool. So earlier we showed the recursive solution for find that does path compression, and it's 3 lines of code. Here would be the iterative solution of find that uses path compression, which is a lot more than 3 lines of code. This one might be a little more easy to understand and convince yourself that you understand. But the elegant solution is so pretty. So you can use either one. In this lab coming up, you're going to have to do, in the autograder, you're going to have to do union find. So when you implement union find, you can reference these lab slides. And when you do the find operation, you can do it recursively or iteratively. Either one works. Just make sure that you do use path compression. Otherwise, it'll be too slow. Okay, so we talked about how find has an O of n complexity when you don't use path compression. Right? Worst case O of n. So what is the average case when you do use path compression? Well, it pretty much becomes O of 1. So it becomes this Ackermann function, which grows very, very slowly. And you can essentially think of this like O of 1. Which is pretty crazy that, it's very optimal, right? That you could do a find operation in O of 1 time. You could figure out whether or not 2 elements are in the same set, because that's ultimately why we're doing this, right? To figure out if 2 elements are in the same set using find, And you can figure that out in O of 1 time. Or I guess to be more precise, Ackermann function, the inverse Ackermann function. And that's really it. Finally, let's talk about union. So that was essentially the find. If you want to find the ultimate representative and use path compression so that you get this crazy awesome complexity. So union is the second function, and you use union when you want to combine two elements to be in the same set. So if you have two elements, and they're different sets, if you want to put them into one set. So here, we have two sets. We have the set here and we have the set here. And you can see that in the representation of the vector. Node 1 points to 0, 0 points to 0, and these all point to each other. So what if we wanted to union 0 and 2? So we wanted to put this one in the same set. How do we do that? Anyone? Well, in the code, 0 points to itself and 2 points to itself. That tells us that they are both their ultimate representatives, right? How do we put them in the same set? Remember that first example we went over where we're like, hey, what if we have these Canadian citizens and these US citizens and we want to make them all US citizens? So to put it simply, really 0 or 2, they are both ultimate representatives. So we can set one to be the other one. So we could either say, 0, instead of pointing to yourself, you're going to point to 2, or 2, instead of pointing to yourself, you're going to point to 0. Either one is fine. And you'll notice that now that we pointed one ultimate representative to the other set, now all of these are also joining that other set. Because if we want to figure out what 4 points to, 3, it'll go to 3, then it'll go to 2, then it'll go to 0. 3 will go to 2, to 1, or to 2, to 0. So that's how you do it for if they're both ultimate representatives. What if we wanted a union 0 and 3? Then what do we do? Anyone? Union means combine the sets. So we want to make 0, element 0 and element 3 to be in the same set. But I guess all the other elements in the same sets, all the other elements in 0 and all the elements in 3, we want those to all be in the same set too. So not only do you want to take that one element, but you want to take all of the other elements in the set and combine them. Because right now, we essentially have two disjoint sets and we want to make them one set with this union operation. Anyone have an idea how we can merge these two sets given the union of 0 and 3? So, what if I just did this? Does that work? That's what we did before, right? We just pointed 2 to be pointing at 0 rather than itself.
Yeah, that makes sense.
But then what happens to 2? We kind of cut it off, didn't we? If
Oh,
this
because
was the
it's not-
case, what's up?
Oh, nothing. I was gonna say because it's not pointing at anything anymore. Like we moved it.
Well, it's pointing to itself.
Well, yeah. But like nothing is connecting it to.
Right. So really what this would do is now this would make it so you still have 2 sets. You would have a set of 2 by itself and then all of the other elements. That's not what we want. We want to union them all together. So similar to when we said union 0 and 2, every time we want to union 2 elements, you have to find those elements ultimate representative and union the ultimate representatives. So similarly, like if I want to union 0 and 4, I have to find 4's ultimate representative and union those. Because otherwise, we're going to cut off our chain. We have to union the leaders. Does that make sense?
Yeah.
Cool. So how do we do that in code? Remember that find finds the ultimate representative. So all we do with union is we just take, reps, which is our vector, find y equals find x. Find x is the, alt rep of x. Find y is the alt rep of y. And you just say, okay, the alt rep of one now points to the alt rep of the other. And that's all union is. So you have 2 functions, you have union and you have find. Using these 2 functions, you can take disjoint sets and figure out, if elements are in the same set or different sets. You can also take sets and combine them into one set. And it's very good complexity, runtime wise. And that's it. As I said earlier, see the lab slides for info on pairs or tuples or functors. And then quickly, the handwritten problem this week. Given n ropes, you want to find the minimum cost of connecting these ropes into one. So, for example, the cost, the cost of connecting 2 ropes is the sum of their lengths. So as an example, let's say that you have these 4 lengths, and this represents 4 different ropes, and we want to connect them all to one rope. There's multiple ways to connect this. You could connect these ones first, and then these ones, and then these ones. But you'll find that if you want to minimize the cost of connecting them, and the cost of connecting 2 ropes is the sum of those 2 ropes of length, the optimal way of doing this is at any given moment, taking the 2 smallest length ropes, the 2 smallest ropes, and connecting them. So using that hint, if at any given moment you want to connect the 2 ropes of the smallest length, think about how you can solve this. And that's it. That's lab this week. Sorry that this actually took 2 hours. This was a pretty long lab. But I hope that, this helped you guys better understand priority queues and union find. And thanks for coming.